Hi students, so this video I'll be talking about processes and threads. The objectives for this video, we're going to learn and understand about Linux processes, understand about Linux threads, and also introduce interprocess communication, or IPC. So a Linux process is executable object code that's running on hardware, and often the encapsulation of that object code is in what's called ELF format, or executable and linkable format. So this is what ultimately the binary that you're using to execute and run on any operating system, but in the case of Linux, on a Linux operating system. So for a Linux process, the necessary resources that are needed to run are managed and allocated by the kernel through the system call interface that we've discussed in previous lectures. So for instance, timers or files or any type of hardware access, it's all organized and managed by the kernel through these system calls. A Linux process is referenced by a process ID, so that's something that you can use to interact with the process, so to send it signals, to stop it, for instance. And a process is going to run on what's referred to as a virtualized processor and a virtualized view of memory. So what does that mean? It means that from the process's perspective, it appears to have its own dedicated RAM and CPU. It doesn't know about any other processes that are running in the system, but in reality, it's being time shared by the kernel. So what a visual depiction here of what we mean by having virtualized processor and memory. Again, from the process's perspective, it just sees a chunk of RAM that it has access to for the storage of its data, and it has access to a CPU and it's executing over time, and it doesn't know anything about any kind of time shifting that's happening. But in reality, what's happening is that the process RAM might be physically split in different locations in physical RAM, and the process CPU is getting time split with other processes that are running on the system, and it's not really running continuously in time. So a process is made of one or more threads, and a thread is a unit of activity within a process. So if you use, by default, if you just compile a Hello World application, you have one process and you have one thread, and your application is referred to as single-threaded. If you specifically start other threads, as soon as you start the second thread, you'll be what's called a multi-threaded application. So in a multi-threaded application, every thread's going to have its own stack, which will be storing local variables. It will be storing the call stack that's used. So for instance, if you call a function or some set of functions, that'll be tracked inside the call stack for that specific thread. And so it'll have the processor state and the current location for a call tree in a specific call stack for that thread. And an important distinction between Linux threads and Linux processes is that while I mentioned before, every process has its own virtualized view of memory and appears to have its own memory isolated to itself, the memory for threads is shared. So every thread within a process has exactly the same memory space. So if every process has its own virtual memory, but every thread shares virtual memory, then how would you share memory access between threads? So if you wanted to access a global variable between two different threads, you could just access it directly. However, you need to think about if you're modifying it from one thread and you're reading it from another thread, if you want to make sure that you have a consistent view of that memory, you're going to have to use synchronization. And we'll talk about different synchronization strategies later in the semester. By comparison, if you're sharing memory between different processes, that's not just built in like it is with threads. Because every process has its own virtualized view of memory, you won't be able to, for instance, access a global variable that's in a different process by default. However, there are different mechanisms for doing that, and those are called interprocess communication, which we'll cover a little bit today, and we'll get into a lot more detail later in the semester. So the Linux signal is one of the simplest ways to do interprocess communication. So a signal is just a one-way asynchronous notification that can be sent from the kernel to a process. It could be sent from one process to another process, or it could be sent from a process to itself. And the process can set up a signal handler that controls how a signal is responded to. So there's a chunk of code you can define that says if a specific signal occurs, do this action. So for example, a common signal that you might want to handle would be Control C. So if you've ever run an application on a Linux terminal before and wanted to stop, you've probably used the Control C key. What you're doing there is sending a SIGINT to stop the process. And your code can add a signal handler that handles that SIGINT and does things like shut down resources and gracefully close. So if you write a signal handler or use a signal handler, you must use signal safe functions that are safe to call asynchronously. And why is that? It's because there's no guarantee of any kind of synchronous capability when you hit Control C relative to what's running in your current code. So if you're calling some function in your running process and you hit Control C and your signal handler calls that same function, you need to make sure that that function is safe to call in two different contexts at once. So one of the easiest ways to do that would be one of the easiest ways to break that capability would be to access global variables. And if you're accessing global variables in a non-consistent way between two different functions that are asynchronous, that wouldn't be a safe thing to do from a signal handler. So you have to keep in mind when you write these that process code can be interrupted at any time by a signal, and your signal handler could be invoked at any time. So IPC more generically, or Linux Process Intercommunication, allows the processes to exchange information without having that global memory space. So processes keep their own virtualized view of memory, but they can still exchange information with each other. And there are several different IPC mechanisms that we'll get into more detail about a couple of these later in the semester, but pipes, semaphores, message queues, and shared memory are all examples of ways that you can do interprocess communication in Linux.